All right, hey everyone, welcome back to another lecture for linear algebra. So today we're covering section 3.6, which is linear transformations. It's about time. Linear transformations are kind of one of the main things that you'll do with subspaces in linear algebra. So yeah, we'll dive right in. The idea behind linear transformations is that, so think back to what you know about functions. What does a function do? It takes in a number and it assigns it a unique other number, right? It has to do like the vertical line test. So there's one, for every input that goes into a function, one output comes out. We're gonna take that notion and extend it. So we'll start with just what is a transformation in general. What we do is we take some kind of vector, stick it into a transformation of some kind, and then some vector will pop out. Okay, so we're going to use matrices as our main source of transformations, but this is the idea. We're extending the notion of what is a function. Okay, so let's take this matrix A as 1, 0, -1, 2, 2, 3, and we'll take our vector, we'll make our input vector v, which is 1, 2, -1. But first, let's just compute the product of this matrix and this vector. And what you get is a column vector, size 2. The first entry will be 2, and the second entry will be 2 plus 4 minus 3, which is 3, like this, right? And notice all we did was multiply them. Well, in fact, let me just go and multiply like an arbitrary vector in R3 by the matrix A, and we'll see what happens, right? There's no mystery what the output's going to be. It's going to be a column vector. It'll have 2 entries, right? The first one is going to be x minus z, x plus 0y minus z. And the second entry will be 2x plus 2y plus 3z. This is the effect of multiplication by the matrix A. So what we want to do is make some kind of function out of this thing. Notice the input, we could have input any, any vector in R3, and it pops out a vector in R2. So what we do is we write t with a subscript a to be the transformation associated with A. Then we have some parentheses, and then inside the parentheses is like the input, just like the notation that we were using at the very beginning, and also just like function notation from like old school, right? However, while technically correct, it's kind of annoying to write parentheses and then brackets on the inside for your vectors and stuff. So it's okay to omit the parentheses. We'll just, and for the rest of this video, we're going to not write the parentheses. They're there, but like it'd be like writing, f of x, but then you just don't want to write the parentheses. So it reduces the amount of writing. Although notice this is like, it's kind of weird, but they mean the same thing, right? And when it comes to writing an entire column of column vector, a bunch of parentheses and everything else, we want the notation to be as clean as possible, right? Okay, and so now the question is, what do we mean by this operation? We just mean, okay, like, what do I want to do when I'm plugging in an arbitrary vector, x, y, z? I just want to multiply it by a. I want it to be this operation. So the output, we already computed. I'll just put an equal sign. It's this. So in other words, whenever someone hands me a vector in R3, for me to transform it using this TA transformation, all I do is subtract the third coordinate of the vector from the first coordinate, and then I double the first two and triple the third one and add them all together. Those are the two coordinates of my output vector. And notice it's a unique output vector. Okay, great. So before we give any formal definitions, I want to just spell out a bunch of vocabulary so that we can start talking about these things. Not just like with this weird, loose terminology. We have words for all this stuff. You can take these as definitions if you'd like. A transformation, also known as a mapping or a function. T, from Rn to Rm, is a rule that assigns to each vector v inside of Rn a unique vector T of v inside of Rm. Okay, it's just a rule of assignment. One input, for each input, you get one output. The space where you're allowed to take inputs from is called the domain. The space where the outputs live is called the codomain. Not range, we'll get to that in a second. By the way, we call T, the notation that we use is T colon Rn arrow Rm. And this reads as T is a transformation or T is a function from Rn to Rm. That's how we say that. So we specify the name of the function or the name of the transformation and the name of the space, which is the domain, and the space, which is the codomain. Those are the things that we give that allow us to reference this function. We also have, usually when we're defining a transformation, we have to say what the rule of assignment is, because there's a lot of ways to transform vectors from Rn to Rm. So we have to specify. Anyway, so just and you'll see examples of that later on in this video. So the output vector T of v, we call that one the image of the input vector v. So let's say, oh, the image of v. What we mean is this guy. Okay. And then now we have to ask, okay, well, what are the possible images of input vectors? That's some space of vectors inside of the codomain. It might not be the entire codomain. It could be that, like, so for example, the transformation given by matrix multiplication like we had, but instead of multiplying by some cool matrix, just multiply by this one. The range of that guy, what are all the possible outputs? You know, you multiply an x, y, z. Okay, this is how we've defined our map, you know, or our function. The input vector goes to, you know, x, y, z goes to the product of the zero matrix and x, y, z. That's going to be the zero vector every time. So the range, the set of possible images for input vectors is just zero. There's no variety at all. But you could have, in our previous example, we'll look into this later on, you can have all kinds of outputs, right? In fact, it'll be all of R2 is the, so in the example that we were just looking at, the range and the codomain are exactly the same. So, and you could have anything in between. You could have a subspace or something like that. So, yeah. Okay, so these are just some words for us to think about. In the example that we had, TA was a function from R3, that was the domain, to R2, that was the codomain. And it was, well, I told you it was the range. We haven't shown that yet. But it was given by, I'll show you the notation that they like to use, although I don't think we'll be using this anywhere else in this video. But they like to do an arrow with a flat, I don't know, like an arrow coming out of a wall or something, I don't know. And then the output will be, you know, a times x, y, z, like that. And we computed what that is. So this is how we specify a transformation. I was very careful to not say linear transformation because, as it turns out, this is not enough to be a linear transformation. Let me now tell you what the actual definition of a linear transformation is. A transformation, or a function, from a t going from Rn to Rm is a linear transformation if the sum of any two input vectors is the sum of their images, and the image of a scaled vector is the scaled version of it, is the scaled version of the image of the original vector, right? However you want to parse this, it's very difficult to say this wrong. The best way to say this is that the linear transformation, a transformation is a linear transformation if it preserves linear combinations. Okay, try if you, yeah, we'll just leave it at that. By the way, if you were to go and verify whether whether a transformation is a linear transformation, you can do both of these at the same time by just computing something like this. Does your transformation satisfy cu plus dv equals ct of u plus dt of v? So what we're going to do is verify that the transformation that we had before is a linear transformation, and we're going to use this strategy. Now, what we're doing here is slightly different from the book. The book goes and checks each of these conditions in the definition one at a time. That can be more tedious, or it could be less tedious depending on the transformation itself, and there's really no way to know which one's better than the other. But yeah, so we're going to do it this way because it's different from what's in the book. And so I highly recommend you trace through the example that the book works out. By the way, before I go and do this, I should mention one other major way that I've diverged from the book here is that this transformation that we're using is a map from R3 to R2. Notice, the inputs are like three-dimensional, or vectors with three components. Whereas in the book, they took in vectors in R2, and the output was a vector in R3. So it's yeah. So and notice the shape of our matrix A is 3 by 2, whereas theirs is 2 by 3. That's the difference. So it's good to also trace through how our example is different from their example. There's a bunch of different ways. Okay. Yeah. So this one is really important to read the textbook. Great. So let's do it. So we want to verify that this transformation T is a linear transformation. Let's go. So we have to check that T times, I'm going to put C x1, x2, x3 plus D times y1, y2, y3 is equal to, okay, what do we want this to be? So notice those are two arbitrary vectors in R3. Okay, we want to check that this is equal to CT of x1, x2, x3. Notice I dropped the parentheses, plus D T of y1, y2, y3. This is what we want to verify. Is it true? Well, we have to go and do it. All right. So what is the rule? Well, first thing we need to do is we have to compute this sum on the inside of the parentheses. So the first thing we're doing is what vector are we actually about to transform? It's going to be cx1 plus dy1, cx2 plus dy2, and cx3 plus dy3. Okay. Now Now, what is the rule? Like, what do we have to do here? This is how t was defined. Well, we have to subtract the third coordinate from the second coordinate, or from the first coordinate. Okay. When we do that, we get cx1 plus dy1 minus cx3 plus dy3. And then the second entry to this vector, this output vector, is 2 times, all right, here we go. 2 times cx1 plus dy1 plus 2 times cx2 plus dy2 plus 3 cx3 plus dy3. Okay. We'll just center this guy. There we go. Now the question is are these two guys equal? Well, we have to do some more work. We're not done. Okay, notice we can, okay, what we'll do first is we'll just distribute everything. So this is, in the numerator, we're looking at, okay, what I'll do is I'll save us some time. In the numerator, or not in the numerator, in the first entry, I'm going to distribute the minus sign and switch the order of the minus cx3 and the plus dy1. Okay, okay, so what that will look like is cx1 minus dx3 plus dy1, sorry, minus cx3. That would have been confusing. dy1 minus dy3. In the second entry, I don't know why I'm calling these numerator and denominator. This is the first and second entry of a column vector. Okay, what we're going to do is distribute the 2, distribute the 2, distribute the 3, and then rearrange the sum so that the x's are in front and the y's are not. Okay, so 2cx1 plus 2cx2 plus 3cx3 plus 2dy1 plus 2dy2 plus 3dy3. Keep in mind, c and d are just scalars. They're just numbers, right? And same for x1, x2, and x3. They're variables which are standing in for an arbitrary entries that could, or arbitrary real numbers that make up the coordinates of vectors in R3, right? So there's nothing fancy going on here. Notice though, okay, I can immediately write this as the sum of two vectors. You can check me on that. Just add these two vectors together and you'll get the one that we just had. I can also factor out a c, from the first entry and the second entry, which means I can factor it out front of the entire first vector. And the same for the second. I can take out a d from every single term and put it in the awkward amount of spacing, but I can factor d out of the second vector. But notice this vector is precisely t of x1, and this vector is precisely t of x1, x2, x3, and the second one is precisely t of y1, y2, y3. So I can write this as c t of x1, x2, x3. If you don't believe me, go and use the definition of t to verify yourself that these two are equal. Okay, and dt of y1, y2, y3. But that's exactly what we wanted. That was the condition for t being a linear transformation, and it is. It is. Okay, so now I want to talk about a really cool, if you notice a conspiracy between matrices and linear transformations, yeah, we'll see very shortly that every matrix defines a linear transformation, and every linear transformation can be written as a matrix. So we'll go both ways. So let A be an m by n matrix. The matrix transformation TA going from Rn to Rm defined this way. This is the matrix transformation. What do you do to a vector x inside of Rn? You just multiply it by a. And if it's a vector, if it's a column vector x inside of Rn, then it has n rows in one column. But a is m by n. But m by n and n by 1. Notice the insides match and the outsides form an m by 1 column vector, which is precisely an element of this codomain Rm. Yeah. Okay. Anyway, and the theorem, but we have our theorem is not just saying that like, oh, the matrix transformation is like defined. No. It's a linear transformation, and we can actually prove that just by chasing through definitions. We have to check that it satisfies vector addition and scalar multiplication. Sure, no problem. So the way that we do this is, let's compute TA of x plus y that's a times x plus y. But like matrix multiplication distributes. Oh, you know what? Let's use the same strategy that we had. So I'm going to start over, but to save time. TA of cx plus dy. I believe now what we're doing is different from what the book does. So yeah. Okay. Anyway, so this is now a times cx plus dy. Which is strange. Well, since so right, the main point of this proof is that matrix multiplication distributes. So we can write this. We know just from facts about matrix multiplication that this is CAX plus DAY. That's just matrix multiplication. We can factor the constant out to the front and so on. And that's well, a of x, or a times x, is just ta of x. So this is cta of x plus dta of y. But that's exactly what we have to verify in order to show that something is a linear transformation, that it preserves linear combinations that are taken inside of the domain, right? And so that's it. That's the whole proof. It just doesn't work. Yeah, and that's it. Great. Okay, so let's now take a look at some linear transformations, and these are kind of some not stereotypical. These are some like prime examples of linear transformations that you might see. So we're looking at this transformation f. I'm almost 100% sure f stands for flip, because it's the linear transformation which takes a vector and reflects it across the x-axis. So f of xy is the thing that you get when you negate the y component of that vector. So it's going to be x negative y, right? Well, okay, so now what we can do is we can write this as x, oops, times the vector 1, 0. Okay. Before I do this, let me write it. This is going to be strange. X plus 0 and 0 minus y. So that you can see this is like x times the vector 1, 0 plus y times the vector 0 minus 1. But if you wanted to figure out what matrix we're looking at here, notice this matrix is exactly what you get when you multiply x, y. Goes kind of backwards to do it this way. By the matrix whose columns are just these vectors. So 1, 0, 0 minus 1. This is going to give you x negative y. So A is equal to 1, 0, 0 minus 1. If you wanted a matrix for this transformation, right? And if you had to show that f is a linear transformation, right, you just do what we did before. Okay, so now what I want to tell you for, I'm going to rename this for reasons. Actually, because I forgot to earlier. So R90 is going to be the matrix, the linear transformation going from R2 to R2 given by rotating counterclockwise by 90 degrees. Okay, we're going to have to do that with some geometry. You have some vector. I don't care, it's xy. Yeah. And we want to rotate it 90 degrees counterclockwise. It's like this. You know, we've got some theta. So now this angle is theta. But the whole angle is like theta plus 90, right? What do we know about the x and y components? We know that, this distance is the same as this distance. And we know that, another color, this distance, the distance along the x-axis, becomes a corresponding distance along the y-axis. So, what is R90 of xy? Okay. The x component, the green little line segment, is what was the y component. So in other words, okay, you take the y component of the original vector and move that much in the negative direction along the x-axis. So in the first component, we put minus y. And then what is the y component of that new vector? It's just move in the positive y direction. What you had to originally move in the positive x direction to get to the original vector xy. So you just put an x in the y component. This is bizarre. This is a very strange thing. But using the same trick as before, the matrix A. Well, okay. Let me just write this using the same trick as before. It'll be x times the vector 0, 1, of course, plus y times the vector negative 1, 0. And so the matrix A is going to be 0, 1, negative 1, 0, like this. And if you recognize that as, I don't know if we talked about it, but, well, we're going to shortly. Anyway, so this is a spoiler alert. Actually, I'm not going to tell you. You're going to have to sit tight for the rest of the video in order to see how you might have recognized this. and it's going to show up in like 2 seconds. But first, we have to go the other direction, right? So the next theorem says that if t going from Rn to Rm is a linear transformation, then t can be expressed as a matrix transformation. There's a matrix that you can write down, which does the job that t does when you do like multiplication. And to get your hands on that matrix, all you do is use the transformation t on all of the standard basis vectors, all n of them. When you do, you'll get n columns, and the transformation, since it went from Rn to Rm, it will output a bunch of column vectors with m entries. And so A is an m by n matrix, right? We call it T in brackets, and we call it the standard matrix for T. Okay. Okay, so now the proof is we have to like go and show that this will work for every single vector in Rn. So the strategy is this. First, use the standard basis for Rn to write x as we'll call it, I'll stick with the books' notation, x1 e1 plus x2 e2. This is confusing because actually I really don't like this notation because I just used x1, x2, x3, and so on as like, oh no, that's good. They're components of the vectors. That makes sense. And that's what they are here as well. The xi's are components of the vector x. We'll just write it like this. x1, x2, all the way up to xn. Perfect. Now it's clear what I mean when I write these things down. All the way up to xn en, like this. Okay. So now, what is t of x? Well, t of x is literally just t of this thing. In fact, let's just copy paste it. Right? But t is a linear transformation, which means it respects linear combinations. So I can write this as x1 t of e1 plus x2. Remember, those guys are just numbers, real number, they're scalars, right? X2 t of e2, and so on up to xn t of en. So far, we're making progress. But notice, okay, each of these is like an m column vector. And now I have a bunch of components being multiplied each by the corresponding column vector. By definition, this is the matrix whose columns are T of E1, T of E2, you know, this guy, this matrix, where these are like the columns, right? You get the idea? All the way up to T of En. Almost. It's this matrix times X. We've decided to call that matrix by brackets T, and this vector is just X. That's it. This is, or T, oh, I guess this is, we've also called it A. I should probably call it A as our conclusion. But from now on, I'm going to be calling it brackets T. because that's a really handy notation, let's just say. Okay, so now I want to point out an awesome linear transformation. This is a generalization of the one that we saw with the R90, and it's the one that I almost spoiled. So R theta, the subscript is theta, which is some angle, right? It will be a linear transformation from R2 to R2. Its standard matrix is cosine theta, negative sine theta, cosine theta. Now the book goes and like verifies this. It like goes and proves it. It proves that it is a linear transformation, and it goes and like computes what the standard matrix is. I recommend going and reading that argument, but it boils down to we just ask what does the transformation R theta do to the standard R2 basis vectors? Uh, well, if you want to rotate something by theta degrees, then you want to rotate something that's 1 unit long in the positive x direction. You want to rotate that thing theta degrees. That's like tracing a point around the unit circle, like trigonometry, Sohcahtoa style. And you just trace it theta degrees around, then ask what are its new xy coordinates. It'll be cosine theta is the x coordinate and sine theta is the y coordinate, of course. Right, and so yeah, there's no mystery as to what this matrix does, right? And so, but again, I'm sorry, there's no mystery what it does to the standard unit vectors. And so, but if you know what it does to standard unit vectors, you can compute its standard matrix. So we're going to do that for this second example. Compute the standard matrix for P going from R2 to R2, which is given by P of xy is x0. Now, I will tell you what the letter P stands for. It stands for projection. The idea is you shine a light vertically along the, in the xy plane, shine a light on the vector. What will happen is, and you cast some kind of shadow on the x-axis. Okay, well, what will happen is you'll keep the same x coordinate because the light beams are going vertically. But you'll lose your y component because you're just a shadow on the x-axis. Let me draw that for you. Oh, that's an eraser. If I have some vector here, I'm imagining drawing vertical light beams, right? What survives when I cast my shadow on the x-axis is just the x component of that vector. So the y component is 0 in the output. So now, what do we do in order to compute the standard matrix for this transformation? We just compute what is P. Oops, I gotta go back to white. What is P of 1, 0? And what is P of 0, 1? Well, P of 1, 0 is 1, 0, right? What do we do? The rule is keep the x coordinate what it is and make the y coordinate equal to 0. That's 1, 0. That was not very helpful. But something interesting happens when we try to compute P of 0, 1. When you do P of 0, 1, well, we have to keep the x coordinate the same, but then you have to make the y coordinate equal to 0. The output here is the 0 vector. And now remember the standard matrix, brackets P, is the matrix whose columns are P of 0, 1 and P of 1, 0. So in other words, it's 1, 0, 0, 0. And if you go and try to multiply 2, 3 by this matrix, when you do, you'll get 2, 0, right? It's the action of multiplying a vector on the right of this matrix will have the effect of leaving the x coordinate alone, or the first coordinate alone, and making the second coordinate equal to 0, right? That's what this matrix does. There, I should also mention the book also addresses this example, and then it takes it a step further. It basically says you can project onto any line. Like there's nothing special about the x-axis that we're shining a light onto. You could do any line. So let me just draw. I'll just draw the picture for you, but I'm not going to go through the whole discussion. So I have some coordinate axis. I've got some line that okay, let me make it like not that line, make it this line. And I want to cast shadows onto. I've got some vector. Okay. Now what I do, what projection onto like a different line means, it means your light beams are hitting it vertically. Sorry, perpendicular, orthogonally. Yeah. And what you end up with after doing this process is a vector that's in the same direction as the line that you're projecting onto, and whose length is like the length of the vector that you started with, but just in that direction. Very interesting operation and really useful too. So again, I recommend going through the corresponding section in the book. Now they reference something called uh, proj UV, like this. If you're interested in understanding how this works, there is a section at the end of one of the sections in chapter 1 goes through how this was constructed. It's just a dot product. Actually, let me just tell you. It's u dot v divided by norm of u times the norm of v. So, and you need this in order to compute the projection onto this yellow line or whatever. So just so you know, this is there's a lot of computation involved in this process, but it is an honest linear transformation, and you can compute its matrix. Its matrix is gnarly when you're done. It's got like components of these two vectors squared and stuff in it. It's kind of pretty intense. It's not something that we're going to spend time on in this video. Okay. So now there are two topics left to talk about when it comes to linear transformations. We want to talk about how to compose. You could do composition of functions. Surely you can do a composition of linear transformations. You can. And it's actually kind of amazing. So what happens is, first of all, let me tell you what the definition of composition of transformations is. Start with two linear transformations, T going from Rm to Rn, and S going from Rn to Rp. Notice the codomain of T is the same as the domain of S. That's very important. And if you remember that technicality from composition of functions, probably chain rule, this came up when you were learning chain rule for derivative. You had to have the output of one has to live in the input space of the next one. Otherwise, we have no hope of composing linear transformations, right? So that's really important. Okay, then we say that the composition S composed with T, and we put a little circle in the middle, it looks like SOT. It is not, it is S composed with T. That is a linear that is given by, I'm not gonna tell you it's a linear transformation just yet. It is. But it's a transformation from Rn to Rp given by, what does it do to an input vector v in Rn? Well, do t to it, and then do s to that. Remember, t of v lives inside of Rn. And S takes in input vectors from Rn, and it outputs vectors into Rp. Okay, we'll do an example of this in just a moment. Don't worry. Okay, great. So our theorem, though, says that S composed with T is in fact a linear transformation, and its standard matrix is literally the product of S and T. You take the standard matrix for S and multiply it by T, and make sure that you keep the order in the same order. By the way, you probably have had to deal with this issue in the past, but I must remind you. Notice, even though T is on the right, we do T first, then do S. Same here. If I was going to multiply this by V, I do T times V and then S times T of V. Okay? The order does matter because matrix multiplication does not commute, right? Just like function composition does not commute. You definitely had to do that example in like algebra class, right? Compose functions two different ways. You'll get a different one depending on the order that you do it in. Okay. S compose. So we want to prove that this is the standard matrix of this linear transformation. Well, S composed with T of V. Let's go. That's by definition. Oops. That's S of T of V. By definition, that's S of the standard matrix of T times V. But by definition, that is it. That okay. But this object on the inside is just a column vector in Rn. By definition, S of that thing is the standard matrix of S multiplied. Oh, that's confusing. Times the standard matrix of T of V. And then the last step is just associativity. By the associative property, this is just S times T. This is some matrix. It is an M by P matrix. If you check the dimensions of all the matrices in sight, you'll see it's an M by P matrix. And you do that matrix times V. And these things are all the same. So yeah, this is the standard matrix. This is quite the amazing formula. You want to compose two linear transformations and then compute its standard matrix. Just do matrix multiplication. And that's going to be our example. Let's go. T going from, so okay, we're just going to do a computation, right? So T is a linear transformation from R2 to R3 given by this thing. T is going to take the first component and then the negative second component, and then 1 plus 2 times the second component. And then S is a transformation from R3 to R4, given which takes a 3 a 3 vector to this crazy vector in R4. Okay. Let's write down the standard matrices for these guys. It's not so bad because we just have to. We're gonna write these down one column at a time. So we just have to ask, where do they send the standard unit vectors? So we have to ask where where T sends 1, 0. Well, 1, 0 gets sent to take the first component, take negative the second component, then take 1 plus 2 times the second component. Second column is going to be where does T take the vector 0, 1? Well, 0, we take the first component, which is 0, take negative the second component, and then take the first component, which is 1, which is 0, plus 2 times the second component. This is the standard matrix for T. For S, okay, this is going to be significantly more work. Where does it take? Okay, there are three standard basis vectors in R3, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. So we're going to do these ones a little bit faster. 1, 0, 0, where does that go? 1, 0, 1, 1. Okay. 0, 1, 0, where does that go? 2, 2, 0, 2. The third one, 0, 0, 1, that basis vector, where does that go? 0, 3, 3, 3. Very interesting standard matrix. And now the matrix for S composed with T, remember, is just S times T. That's our formula, our theorem, which is 1, 0, 0, negative 1, 1, 2 times, oh, that's got to be on the right. I almost got the order backwards. 1, 2, 0, 0, 2, 3, 1, 0, 3, 1, 2, 3. We want to multiply these. So first of all, what is the size of the output? This is a, oh man, okay, this is a 4 by 3. This is a 3 by 2. So our output is going to be a 4 by 2 matrix. Let's put that right here so there's enough space. Now we go and do the computation, and I have to warn you, I haven't worked this out beforehand, but it shouldn't be so bad. These columns multiply nicely. We're looking at 1, 3, 4, 4. And then the second column, right, I just did this column times each of the 4 rows. Now I'll do this column times each of the 4 rows. I'm getting negative 2. Negative 2 plus 6 is positive 4. Then positive 6. And then another 4. Final answer. Just was a matrix multiplication problem in disguise. So that's kind of fun. So last thing that we need to talk about, just like we talked about for matrix multiplication and things like that, we had to talk about inverse matrices. Now we're going to talk about inverse transformations. The gateway to this is to think about, like, okay, what is a transformation doing? It's transforming one vector into another one. We saw that with counterclockwise rotation by 90 degrees, that R90 matrix. What did it actually do? It took every vector in the plane and rotated it 90 degrees. Okay, I can undo that process. Just take every vector in the plane and rotate it by 90 degrees clockwise, the other way, right? And sure enough, notice if you compose those matrices, even if you do, like, first of all, counterclockwise, then clockwise, or clockwise, then counterclockwise, doesn't matter. You're whatever vector you start with, you're just going to rotate it 90 degrees and then rotate it back 90 degrees. It's going to end exactly where it started, right? And so the output of the composition of those two matrices is like the same as the input for every vector. Every vector has this property. Okay, that's a property of the composition, right? And it has it's the idea is that one of the two transformations is undoing the process of the other one. Okay, so we'll give first of all a definition for the identity transformation. The identity transformation is the do nothing transformation. Notice it takes an input vector, and for every vector that it takes in, the output is that vector itself. That's the identity transformation. Generally speaking, we have one identity for each n. And if we want to specify the value of n, we'll write it as a subscript. Sometimes we don't. Sometimes we'll just, like, listen, it's n or whatever. And so we won't write it. In this case, we're looking at I2, whatever. Okay, so now for inverse transformations. So let S and T be, both of them, notice, go from, they're both their standard matrices are square. We'll call it that way. They're transformations, linear transformations from Rn to Rn, such that exactly the property that we saw in our observation holds. If you compose them together, forward or backwards, you get the identity transformation. If that's the case, then we call them inverse transformations, and we call the transformations themselves invertible. Now you might think like, hey, there's got to be a relationship between these and inverse matrices. Yeah, that's our last theorem, which is let T going from Rn to Rn be an invertible linear transformation, then the standard matrix for T is an invertible matrix, and the standard matrix for the inverse transformation is the inverse of the standard matrix for the transformation. Let me say that again. In the standard matrix for the inverse of the transformation is the inverse of the standard matrix of that transformation. That's what this means. Again, it's a great formula. Just super nice. So we want to compute r of negative 90. Now remember, r90 was this guy. It was 0, negative 1, 1, 0. We want to compute that thing's inverse. Well, the formula for the inverse of a matrix is just the it's one right 1 over AD minus BC times DA negative B negative C. Flip the 2 on the main diagonal and negate the off diagonals. So this is okay, so R of minus 90. Oops. Standard matrix all around. Okay, so 90 degrees clockwise has standard matrix. Well, AD is 0. BC is negative 1, being subtracted is positive 1. So this is 1 over 1 times, we have to flip the locations of the zeros, 0. And we have to negate the off diagonals. And if you go and multiply these two matrices, you will get the identity. Okay, so that's enough for now. This is an overview of linear transformations. There's more to be said, but most of what's left to be said is a deepening of some of these connections and observations, kind of tying it back to some of the things that we've talked about and pushing forward onto other things. So moving forward, we'll be skipping section 3.7. However, for those of you who are interested in applications, I have to tell you, section 3.7 is hands down the best section for applications. It's it's got like Markov chains and like a lot of like enumerative problems, and like you can like iterate matrices and find some really cool examples in there. So if you're finding it's like, oh wait, but like what are some applications of like all the stuff that we're learning about? You'll find a lot in that section. Unfortunately, it's pretty long and we don't have time to cover it. So next time we'll be starting with chapter 4, and we'll be starting to talk about eigenvalues and eigenvectors, which are also very, very highly applicable out in the world. So yeah, I will see you in the next video.